Good afternoon, Professor.
Hi, nice to see you. Let's wait a couple of minutes, maybe more people will join. Okay, so we continue today discussing um, thermodynamic related topics. And so we introduce the concept and define what is temperature, how temperature affects on the size of bodies, so the thermal expansion and construction. Also considered some unique features of water in terms of thermal expansion, like density dependence on temperature. And now let us continue with gases. So let us consider which are the most important parameters which define the state of gases. We will consider define some system which we are going to consider, and also go through some experimental evidences which can be experimentally measured, and based on these different experimental dependencies which are observed for gases systems, we will proceed with some general equation which describes properties of the state of the gases, including these macroscopic thermodynamic parameters. Okay, so maybe let me change the screen. And most of gases under not very high pressure, the interaction between molecules or atoms is very small. And for most cases, when gases are so-called diluted, not at high pressure, we can neglect with their interaction. So there is only one type of interaction between, let's call it particles, which form the gas. It's only when they move in space and collide with each other. So this is the only way how they interact with each other. And in this case, if this definition is true, we can call this gas, the system, as ideal gas. So because this interaction is either very small or completely negligible between particles which form the gas, in the case of ideal gas, gases, they don't have some defined shapes or forms. They always occupy whole volume of the container, which constrains them. So that's why we cannot operate with this equation. For instance, we were considering a change in volume as beta, like volumetric thermal expansion coefficient times initial volume times change in temperature. So for gases, it's not applicable. It can work only with liquids and solids. Because for gases, we don't have this initial volume. It always occupies whole volume of the container. So some different approaches should be applied. So in dealing with ideal gases, it's convenient to specify the amount of material, the gases which we have in our system with so-called like in moles. So moles are defined as mu equal to the ratio between mass and molecular mass. So molecular mass is defined as an atomic number of chemical element in grams per mole. So it's measured in molecular mass units, grams per mole. So 1 mole of any substance includes or consists of a given constant number of particles, like atoms or molecules, which is Avogadro's number, and this is 6.22 times 10^23. So this is amount of molecules or atoms which form 1 mole of any substance, including ideal gas, which we are considering now. So this is a convenient form to deal with the amount of material we have. And now we will consider 3 most common processes, kind of very like reference processes for ideal gases, which were observed experimentally, and we have these relationships which we are going to, simple relationships which we are going to deal with. They were not derived from anywhere. It's just experimental result. Some summary of many experiments. So let us consider some system like cylinder with a piston, which this volume is filled with gas. So there could be 3 main processes which are going on. So first one is isothermal, means process with constant temperature. So when the gas is kept at constant temperature, its pressure is reversely proportional to volume. It's so-called Boyles Law. And we have first case, temperature is constant, then it states that pressure of the gas is proportional, like reversely proportional to volume. From here we can, let's say, write that the product of pressure and volume is always constant. So if we compare 2 different states of this gas, like state 1 and state 2, and the process of going from state 1 to state 2 was isothermal at constant temperature, that we can write that P1 times V1 is equal to P2 V2. That is the Boyles law. So now let us consider another case. This is so-called isochoric. So sorry, this will be the last one. Let's go for isobaric process when we have pressure constant. So in this case, if pressure is kept constant, the volume this gas occupies is directly proportional to the temperature. So we can write that for isobaric process, volume is proportional to temperature. In other form, we can write that the ratio between volume and temperature is constant. So means, again, if we compare two different states, when we go from state 1 to state 2 with isobaric process, we can write such equality. V divided by T, V1 divided by T1 is equal by V2 divided by T2. So, and now we go for the, this law is called in English literature, Charles law. There is some discrepancy with English and Russian literature, so be aware of this, because it is not very clear who was working on what and on which dependencies. However, in English literature, this is considered to be Charles law. And there is the last one, which is also very important and should be considered. The third is so-called in English literature again Gay-Lussac law, and in this case we deal with isochoric, or in other words, isovolumetric process when voltage is constant. Sorry, voltage. Volume is constant. It's too fast to go to voltage. That will be next semester. So volume, I'm accustomed to deal with voltage. That's V is kind of intuitively voltage for me. So volume is kept constant, and in this case, we have pressure directly proportional to temperature. So similar to the previous one, but instead of voltage, we have pressure proportional to temperature. Again, the ratio of pressure to temperature is constant, and if we compare two different states of the gas, so P1 over T1 is equal to P2 over T2. So all these three relationships which we considered already can be very helpful to solve a wide range of problems in which are related to ideal gas. So very useful and simple. So by summarizing these three laws which were obtained experimentally, we came up with so let's say kind of general law of ideal gas, and like equation which describes the state of ideal gas, because it involves all three state parameters, which is pressure, voltage, and temperature. So the general, this equation for the state of the ideal gas, or in other words, it's called ideal gas law, is P times V, pressure times voltage, sorry, not voltage, volume is equal to nu, like number of moles of material which we deal with, times R times T. So we can write in a bit different form with more details. Will be mass divided by molecular mass times R times T. So we have a new term here, which is this R. This is a constant. And if pressure goes to approaches 0, the ratio P pressure times volume divided by nu times T approaches this constant value R for all gases which satisfy condition of ideal gases. So this, if we consider pressure in pascals, which like 1 Pascal is who remembers what will be the definition of Pascal? It will be what, 1 Newton per
meter square.
Meter square, yeah. So we have, if we deal with these units, then for the it's so-called gaseous constant or universal gaseous constant equal to 8.314 joule per mole per Kelvin. So this is the universal gaseous constant, and using this value of universal gaseous constant, we also can determine what will be the volume occupied by 1 mole of ideal gas at standard conditions. So we have nu equals 1, temperature is 0 degrees Celsius, pressure is 1 atmosphere. So in this case, this volume will be R times T divided by P. And this is equal to another quite common constant, 22.4 liters. So this is the volume which 1 mole of ideal gas will occupy under standard conditions. So it is quite common and convenient sometimes to define the amount of material, like expressed not in moles, but in number of particles which forms this gas, molecules or atoms. So in this case, we can write that pressure times volume is equal to nu RT. And we know that in 1 mole of any substance, we have Avogadro's number of particles. Then the number of moles can be represented as the ratio between total number of particles and Avogadro's number. And then we have a product with a constant R and T. So if from here we substitute the ratio R divided by Na, the Avogadro's number, so we have ratio between two constants, universal gaseous constant and Avogadro's number, we get another constant, which is very important constant and goes beyond molecular physics. It is widely used in solid state physics, physics of semiconductors. That is Boltzmann constant, Kb denoted. And this is equal to 1.38 times 10 minus 23rd power joule divided by Kelvin. So in this case, when we substitute this ratio R divided by Na by Boltzmann constant, we can write the ideal gas equation as PV equal to total number of particles times Boltzmann constant times absolute temperature. So this is another form of this ideal gas equation, which can be very useful in cases when you deal with number of particles or concentration of particles, etc. Then you don't need to calculate number of moles and go for that. Okay, now let us proceed further and consider heat and make internal energy, give more clarifications to these concepts. So internal energy of a system is considered like whole internal energy of the system with respect to which associated to its macroscopic components like atoms and molecules, and is determined from relatively to the reference frame at the rest, which is located in the center of mass of this system. So this definition, when we consider it with respect to this reference frame at rest, located or originated at the center of mass, excludes possibilities to add some kinetic energy of the, like some bulk kinetic energy of the translational rotational motion of this system to the internal energy. So that is the way how we define that this internal energy is determined only by the macroscopic components, not by moving the system as a bulk somewhere in the space. And heat definition. So of heat is the transfer of energy. So it's not energy like internal energy, just transfer of energy across the boundaries of the system due to some temperature difference between the system and its surrounding. So when we are talking about heat, means that we either transfer some energy from the surrounding inside the system, or we dissipate this energy from the system. It comes out through its boundaries to the surrounding. Of course, it depends, these directions, they are defined by the temperature gradients, which is the temperature difference between 2 points divided by the distance between these 2 points. So initially, when it was not so clear relationship between heat and work, some mechanical work, people considered that heat, like transfer of energy from one system to another, can happen because of flowing of some imaginary fluid called caloric. And that's why historically heat was measured in calories. So it's like calorie, and this is energy which is required to heat 1 gram of water from 14.5 to 15.5 degrees Celsius. So it's actually heating up of gram of water per 1 degrees of Celsius. However, it's specified the temperature range because heat capacity, we will talk about this a bit later, depends on temperature. So we need to specify some temperature range to be accurate. But once Joule have shown in his experiments that there is a direct relationship between heat, which like some energy transferred to the system or from the system, with the mechanical work, like work of some friction forces, which are as we learned before, non-conservative forces, then it became obvious that there is a direct relationship between calorie and joule as a unit of energy. So it was shown that 1 calorie is equal to 4.186 joule. And since then, it's quite common to deal with joules for thermodynamic systems. However, calories are still in use, and specifically calories are used in evaluating, quantifying energy of energetic value of food we consume. So usually it's not in joules, but in calories. Or I mean, in kilocalories, because calorie is not a big value of energy by itself. So now let us define what is heat capacity. We mentioned about this, and heat capacity defines the is defined as the amount of energy, which is denoted as Q, capital Q, which is needed to rise the temperature of the body or of the system by 1 degree Celsius. So you can write that Q is equal to capital C times delta T. So this capital C is heat capacitance of the system. If you want to change its temperature by delta T, you need to multiply it by heat capacitance, and this will give you the amount of energy you need to provide to reach this change in temperature. So it is more reasonable to deal with specific heat capacity, which is like C is equal to this capital C divided by mass of the system, because then we can not be fixed to specific size of the system. It just defines property of the substance itself. And in this case, we can write that Q is equal to specific heat capacity times mass times change in the temperature. So assuming that we neglect with the external extension and or construction and the heating and cooling respectively, when some work is done either against atmosphere or by atmosphere for this increasing and decreasing in volume of the body, we can write that change in internal energy will be equal to this provided energy to the system. And also need to underline that when we change temperature from T1 to T2, total energy provided to the system will be integral of in the range from T1 to T2, C times, here we can put mass, since it doesn't change in the process, but we have specific heat capacity times delta T. So we keep this specific heat capacity in the integral, like under the integral, because specific heat capacity is a function of temperature for all systems. If temperature changes in a wide range, this should be taken into account, and you should consider heat capacitance as a function of temperature. So there is such so the question is, how do we define this heat capacitance? For instance, we have some unknown substance, let's say some substance with unknown heat capacitance. We pick up some mass of this substance with heat capacitance Cx, which we don't know. Then we heat it up to some temperature, which we can measure. And then we consider some big volume of water, which is much bigger than the volume of the container for water. So we can neglect with the container effect. Then we have some mass of water, heat, specific heat capacitance of water, which is known, and temperature of water, like initial temperature. Then we put this material with unknown heat capacitance, but known mass and known temperature in this volume of water, and let the system come to the equilibrium, several equilibrium. So this will end up with some final temperature Tf. And we can write that amount of energy which is gained by cold substance. In this case, it's water, let's say, will be equal to the amount of energy which was lost by the hot substance. So for this case, we can, assuming that we already know the relationship between energy and specific capacitance, specific heat capacity, mass, and change in temperature, we can write such equation. We'll have mass of water times specific heat capacity of water times difference in final and initial temperatures of water equal to minus mx of this mass of the material which we want to investigate in terms of specific unknown specific heat capacity C times Cx times difference between the final and initial temperature Tx. So since all parameters besides Cx are known, we can determine this unknown heat capacity of the substance under investigation. So there is another thing we need to highlight. It's latent heat. So we can write that Q is equal to the product of this so-called L, like capital L is latent heat delta M, and this is associated with phase transition. So for instance, we have water, let's say, we heat it up to boiling temperature, it starts to boil. So boiling is evaporation of water, but not from the surface, because evaporation is just evaporation from the surface, but it's evaporation from the volume. That's why we see these bubbles which are coming out from water when it's boiling, because it starts to evaporate from whole volume. And this is actually phase transition between liquid and gaseous states of water. During this process, temperature doesn't change, because all provided energy, like this heat which system is gaining, it is going for this latent heat to realize phase transition from liquid to gases. And this amount of energy can be calculated as latent heat, this capital L, which is determined by the material and by the aggregate state, times amount of, like, times some mass, which we convert from one aggregate state to another. So if we consider now some plot will be energy in joules, which we provide to the system. And here will be temperature in, let's say, degrees Celsius. So let us consider that we start with some ice at negative 30 degrees Celsius. So here we have temperature minus 30 degrees Celsius. and we start to provide some energy. It gains heat. So temperature of ice will increase and will reach 0 degrees Celsius. So this is temperature of phase transition between ice and water. And that means that once we provide further some energy to the system, its temperature will not change. And we will just have some, so here is only ice. Here we will have ice plus water. Then it will reach will gain enough energy to convert all ice to water. And once we don't have any ice left, we will proceed further with the increase of temperature. And it will continue until this rise in temperature reaches 100 degrees Celsius. Then we will again be in, so here in this region we have only water. And here we will reach the boiling point and cause phase transition from water to vapor. That's why our temperature will not change with adding some energy to the system. That will go for latent heat until all water is vaporized. We get only water vapor, like steam. So in this region, we have water plus steam. And then we will increase temperature of steam with providing more and more energy until our container will explode or we stop providing energy. So each of these segment it behaves differently and is defined by different features. So let's call this is like A, B, C, D, E segments, and here this processes will be defined by heat capacitance of ice, specific heat capacitance of ice. Then here we will have latent heat of, let's call it 1, of conversion ice to water. Not seeing that it's 1. Then for the segment C, we will get heat capacitance of water, C omega. Here we have latent heat 2, which is conversion of water to steam, and heat capacitance of steam. So in during the segment A, like part A, we provide to the system energy, which is equal QA, and this is defined by mass of ice times specific heat capacitance of ice, and change in temperature. And this change in temperature is 0 minus 30. So we consider final temperature minus initial temperature. So we go from minus 30 to 0 degrees Celsius. Then we have part B, will be QB is equal to latent heat 1 times mass of ice, because we convert all mass of ice to water, That's why latent heat of ice times mass of ice. And here we don't have any change in temperature. Delta T is equal 0. So part C, we have energy QC, which is the product of mass of water times specific heat capacitance of water and change in temperature. Again, change in temperature is going from, final temperature for water is 100 degrees, like -0. Then we have part D. QD is also phase transition. So we have latent heat 2 of water, conversion to gas, and mass of water. Again, delta T is equal to 0 here. And part E, QE, is equal to mass of steam. We already converted all this water to steam, times heat capacitance of steam times delta T, which is some unknown maximum temperature we reach, -100 degrees Celsius. So this is step-by-step consideration of warming up ice, then phase transition ice to water, then warming up water, phase transition water to steam, and warming up steam. This, of course, can be applied to different materials, like different substances. Of course, all these specific heat capacitance, latent heat, and temperatures at which phase transitions are observed, they will be changed for they will be different for different substances. So this particular example is for water. Okay, so next what we want to consider will be work and heat in thermodynamic processes. So we are coming closer to this first law of thermodynamics, which will be introduced quite soon, but I believe that we will do it already next discussion, and consider some applications of this first law of thermodynamics, which is nothing else as specific form of law of conservation of energy, which is applied to the internal energy, heat and work. And also we'll consider more in details ways how energy can be transferred. So we will discuss thermal conductivity, conduction, and radiation as mechanisms of transferring energy. So this is going to be the topic of our discussion for Friday. And yeah, now you're welcome to ask questions if you have any.
Excuse me, Professor, can I ask questions?
Mm-hmm. Sure.
So in the during the analysis of last graph that you plot, so there are
which graph? Can you repeat?
From like phase transitions of water.
Oh, okay, yeah, sure. That's
so in cases, yeah, in C and in D cases, when we have water and water plus steam, masses of water did not change. And can we consider that from first transition from ice state till the steam state, mass of whole water did not change? Or are we considering taking into account that mass is distinct and different?
So if we consider this particular case, let's say as a closed system, then we consider that mass doesn't change. So it's just mass of ice and mass of water, but total mass doesn't change. And in closed system, as we mentioned at the end, so we can warm up steam further. So that means that steam doesn't go away from the system. So it's closed system, then masses should be the same. Yeah.
From ice till the steam.
Yeah, till the steam. So technically you could have reversed this process back, not provide energy, but take energy away from the system, and you should have end up with the same amount of ice as you started with.
Okay, thank you.
Yeah. However, of course, if you consider just parts of these processes for different systems, then you need to be careful what is mass of ice, what is mass of water. But for this particular example, yeah, we deal with a closed system where a total amount of water doesn't matter in which aggregate state it is, doesn't change.
Okay, thank you.
Okay, thank you for question. Okay, guys, thank you for attention. Have a good evening and see you on Friday.
Thank you very much. Have a nice day.
Bye.
Goodbye.